Before we dive into today's episode, make sure to hit that subscribe button. It's the best way to stay updated with our latest insights.
Ladies and gentlemen, welcome to the CTSS Academy podcast. The energy is electric. The crowd is alive. Let's dive into greatness. We're champions strong.
Before we start the show, don't forget to check our new ebook, Kill All Bugs, Learn Software Testing in One Day. For a limited time, it's only $9.99. Links in description.
Welcome to the Deep Dive. Our mission today is a journey, really. A journey from the kind of ecstatic headline you see every day to the cold, hard scientific reality.
Yeah.
We are taking one of the most tantalizing ideas in modern astronomy, this concept of Earth 2.0, and we're going to put it through a pretty serious reality check.
And it's so important that we do this because the language we use around discovering these exoplanets, it's saturated with optimism.
Right.
So today we're going to look at the facts. We'll examine the single most similar planet ever found and drill down into a pretty surprising question. Why is our best possible cosmic twin, at least on paper, almost certainly a completely uninhabitable hellscape?
Okay, let's unpack that. And to do it, I think we have to start with the historical scope because the context here is it's staggering.
It really is.
Think back just 35 years, it's 1990. Carl Sagan has the camera on Voyager 1 turnaround to take that famous pale blue dot photo. At that moment, we knew of 9 planets, that's it. And they were all in our solar system.
All orbiting our sun. The rest of the galaxy was, it was all theoretical. The idea that planets even existed around other stars was basically science fiction.
And then everything changed.
Everything. The breakthrough discoveries, they started trickling in around 1992 and then just exploded after 1995. And it tore the curtain down.
Sure.
Suddenly, we weren't alone in having planets.
And the rate of discovery since then is what truly blows my mind.
Oh, it's absolutely mind-boggling. We've gone from, a theoretical 0?
Yeah.
To now having formally confirmed over 6,000 exoplanets.
6,000.
And for the last decade, we've been averaging the discovery of one new exoplanet pretty much every single day. Missions like Kepler and TESS, they've just opened the floodgates. It's a universe that's suddenly filled with worlds.
So with 6,000 planets out there, we're constantly seeing these headlines, right? Earth-like, Earth 2.0. But what does that similarity really mean? If you could, just instantly teleport to the planet that's rated the highest for Earth-likeness, would you find paradise? Or would you find the biggest disappointment in astronomical history? That's really the core tension we're navigating today.
And to navigate that, we have to start with our current frontrunner. We need to introduce the planetary system around a dim little star called Teegarden star.
Teegarden star. Okay, it sounds a little whimsical, but it's real and it's close, relatively speaking.
Very close. Just 12.5 light years away in the constellation Aries. And the star itself is tiny. It's what we call a red dwarf or an M dwarf. It only has about 9% of the sun's mass.
And how did we even find planets around a star that small?
Well, the discovery in 2019 was indirect. You don't actually see the planets. Instead, astronomers were watching the star and they noticed a rhythmic.
A wobble.
A wobble. Yeah, a tiny wobble in its movement. And that tells you that something massive and invisible is pulling on it gravitationally. And in this case, it turned out to be 2 things. They're later confirmed as the planets Teegarden B and Teegarden C.
And the real excitement, the real buzz, it's all focused on Teegarden B. So why? What's the big deal with this one?
Because on paper, just looking at the raw data,
Yeah.
it has everything. It's orbiting smack dab in the middle of the Goldilocks zone.
Right, the habitable zone. Not too hot, not too cold.
Exactly. The temperature is theoretically just right for liquid water to exist on the surface.
And it's more than just the location, isn't it?
Oh, much more. The physical stats are incredibly promising. Its mass is only about 5% greater than Earth's.
Wow, that's close.
It's very close. And that strongly suggests it's a rocky planet, like Earth, not a gas giant. It also means the gravity would be, pretty much what you're feeling right now.
So that sounds like we found the jackpot, but I'm guessing scientists don't just go on a gut feeling. There must be a standardized way of scoring these worlds.
There absolutely is.
Yeah.
And this brings us right to the metric that gave Teegarden B all its fame, the Earth Similarity Index, or ESI.
ESI, okay.
It's a scientific scoring system. Pretty simple. It goes from 0 to 1. A score of 1.0 would be Earth itself.
And this is where the headlines come from. Teegarden B's score is, what, an incredible 0.97?
An incredible 0.97. You really couldn't get much closer to a perfect match unless you were actually looking at Earth.
So, what's the catch?
The catch is that this score, while it's exciting, is what we sometimes call the great illusion of exoplanet science.
The great illusion. How can a 0.97 be an illusion?
Because that near-perfect ESI index, it only accounts for a handful of very basic, easily measured things. It looks at the planet's size, its mass, and how much energy it gets from its star. And that's it.
Wait a second. If it only looks at size, mass, and distance, then what's it missing? It feels like it's missing everything that actually makes Earth alive.
It is. It's missing almost every single critical variable for life as we know it. The ESI completely ignores the most important questions.
Right.
Like, does the planet have an atmosphere at all? And if it does, can it circulate heat? Does it have a protective magnetic field to shield it? And maybe the most important question of all, what is the actual surface temperature?
Not just the theoretical one.
Exactly. The real temperature depends entirely on things like greenhouse gases. The index gives us a postal code, a location, but it tells us nothing about the climate or the houses built there.
So the ESI is really just a fancy way of saying rocky planet in the right spot.
That's a perfect way to put it.
If it misses 90% of what matters, why? Why do we even use it?
Because, honestly, it's the best we can do with our current technology.
Yeah.
Those three things, mass, radius, orbital period, those are the things we can reliably measure from light years away.
Oh.
Figuring out if it has an atmosphere or a magnetic field requires much, much more difficult analysis. It's incredibly challenging. So the ESI is a helpful first filter, a starting point. But it is a terrible conclusion.
That makes perfect sense. You gather the easy data first, but it's highly misleading if you stop there. And once you do factor in those missing conditions, especially the type of star Teegarden B orbits, that dream of Earth 2.0 starts to look more like a nightmare.
It really does. We have to dive into the specifics of this system. So let's talk about just how close Teegarden B is to its star. Its whole orbit is incredibly tight. It's about 1/15 the distance of Mercury's orbit from our sun.
1/15. That's practically skimming the surface.
Basically right on top of it. And that extreme proximity, that creates the first fatal flaw.
Okay, what does an orbit that tight do to a planet?
It creates two huge problems, and both come from gravity. First, the year is, well, it's ridiculously short. Teegarden B completes a full orbit, a full year, in just 4.9 Earth days.
A 5-day year. That is almost hard to even conceptualize.
It is. And second, because of that intense gravitational pull, the planet is almost certainly tidally locked.
Tidally locked, like our moon.
Exactly like our moon. We only ever see one face of the moon because Earth's gravity has locked its rotation. Teegarden B is trapped in that exact same gravitational grip with its star.
So wait, if it's tidally locked, does that mean one side of the planet is just baked forever?
Precisely. One face of Teegarden B is in a state of eternal, scorching day. The temperature there could be hot enough to melt lead. Meanwhile, the other side is plunged into eternal, freezing darkness, so cold that the atmosphere itself would freeze and fall as snow.
So life couldn't exist in either of those places. It would have to be in that tiny little sliver between them.
It could, theoretically, only survive in that narrow band, the twilight zone, what we call the Terminator line.
The Terminator line.
Right where the sun is perpetually on the horizon. But even that survival depends on a massive if. You need a very thick, very efficient atmosphere to circulate heat from the hot side to the cold side. Without that, the whole system collapses.
Which brings us to fatal flaw number 2. And this one is about the star itself. Teegarden's star is a red dwarf. We tend to think of small stars as being calm, but the reality is very different.
Very different. Red dwarfs are notoriously volatile. They're prone to these violent fits, these immense stellar flares. They're basically unpredictable explosions of X-rays and radiation.
And we've seen this happen with other red dwarfs nearby, right?
Yeah, we have. A great example is Proxima Centauri, a star very similar to Teegarden. Astronomers watched it unleash a flare that, for a few minutes, boosted its brightness by 14,000 times.
14,000 times. If a planet is orbiting that close, what does a blast like that do to it?
It's absolutely catastrophic for habitability. A flare that powerful is like a cosmic sandblaster. It can literally strip a planet's atmosphere away over time, layer by layer.
So even if it had a perfect atmosphere to begin with,
The star would just rip it away. And without that atmosphere, any oceans would boil off, the water would be lost to space, and your 0.97 ESI twin becomes a barren, tidally locked, radiation-scorched rock.
That one realization, it just completely dismantles the whole Earth-like idea. It shows that just being in the right location it's barely half the battle.
It's not even half. It's like saying a car is perfect because it has 4 wheels. You haven't even checked if there's an engine.
Okay, so let's push this even further. Let's set aside all those physics problems just for a moment for the ultimate thought experiment.
I like this. Let's play the cosmic lottery.
Right. Let's say we win. We find the perfect twin orbiting a perfect, calm, sun-like star. It has magnetic field, it has a thick atmosphere, gravity is spot on, liquid water everywhere. We land, we step outside. What happens?
We might still be in for a monumental shock. You look around, and the oceans, they might not be blue. They might be a murky green full of iron. The sky could be a hazy, thick orange, not blue. And the moment you check your instruments, they'd be screaming one critical warning at you.
No oxygen.
0 oxygen.
If everything else matches, the mass, the temperature, the water, why would the air be unbreathable? Why would it be so different?
Because we didn't find today's Earth. We found Earth's identical copy from 3 billion years ago. We found it during its Archean period.
So all the raw materials are there, but the evolution is just way behind ours. We've shown up 3 billion years too early for the party.
You've shown up 3 billion years too early. That planet might be teeming with life, but it would all be microbial life, anaerobic life, the kind of life that finds oxygen toxic.
And its atmosphere would be toxic to us.
Absolutely. Rich in methane, ammonia, CO2, you take one deep breath, and you die instantly.
And I think this is the crucial distinction we have to take away from this. We don't just need a habitable planet. We need a planet that's habitable right now in its current, very specific phase of evolution.
Yes. Think about the timeline, because this is what I call the tyranny of time. Earth is 4.5 billion years old. For the vast majority of that history, it was completely uninhabitable for a human.
Right.
The oxygen-rich atmosphere we depend on, the one that allowed for complex life to evolve, that only really formed in the last 600 million years or so.
That's less than 15% of Earth's entire history. That's a tiny window.
It's an incredibly narrow window. And if you think about us, modern humans, we've only been around for maybe 400,000 years. That's a rounding error. It's an almost immeasurable slice of time. So if you land on a perfect twin that's just 500 million years too young in its biological cycle, all those perfect ESI scores mean nothing. You can't live there.
So we're really saying that even if you find a world with the right ingredients in the right place, you also have to win the lottery and show up at the exact right evolutionary moment in its 4.5 billion year story.
That's the synthesis. You need the right physics, the right geology, the right chemistry, and the right timing, all to align. The question isn't just, are there habitable planets? It has to be refined.
It has to be more specific.
It has to be, are there planets habitable by us right now, this week?
That complexity, it completely changes how you have to view our own planet. Habitability isn't some fixed label. It's not a pre-made package a planet gets when it's born.
No, it might be the single most sensitive balance in the universe. It's the end result of billions of years of ongoing evolution, catastrophic events, and just countless cosmic coincidences that pushed our planet in exactly the right direction. It's a miracle of timing.
So as we keep searching for other homes out there, the one undeniable truth we have to remember is this. We belong specifically to this process, this planet, and this exact fleeting moment in cosmic history. Understanding that makes Earth so much rarer and so much more precious than any simple 0.97 score could ever suggest. That's a huge thought for you to carry forward the next time you look up at the night sky.
Hey, yo! Haven't you checked out our new book yet? Link in description.
Thanks for listening. If you found value in today's episode, please subscribe and leave us a review. It helps more people find the show. See you in the next one.